Welcome to Two Projects. In this video, we are going to explain the project Plant Disease Detection in Imbalanced Datasets using efficient convolutional neural networks with stepwise transfer learning. Before diving into the execution, let me give you an overview of the project. So, plant disease detection and classification involve the identification and categorization of various diseases affecting plants through the analysis of visual symptoms present on plant leaves or other parts. This process is very important for agricultural management as it enables early detection and targeted treatment, thereby minimizing crop losses and ensuring food security. But traditional methods of identifying plant diseases often rely on manual inspection by experts, which can be time consuming and it is subjective, that is, everyone will have their own point of view, so the decision will be changing. And traditional methods are impractical for large scale farming operations. So, to overcome these limitations, automated systems leveraging computer vision and deep learning techniques are increasingly being developed. These systems analyze images of plants to detect and classify diseases rapidly and accurately, providing farmers with timely information to take necessary actions such as applying pesticides or implementing disease resistant varieties. So, we will be employing computer vision and deep learning techniques for plant disease classification and detection. Now, we will see the workflow. So, the project uses two datasets, plant village dataset and pepper dataset, for training and evaluating the model's performance. So, before training the models, image pre-processing techniques are applied to enhance the quality and variability of the input data before feeding the images into the convolutional neural network models. So, data augmentation techniques are used to create more training data for machine learning models by applying various transformations to existing images. These transformations include actions like rotating the image, flipping it horizontally or vertically, changing its scale, zooming in or out, shifting it slightly, or changing its brightness and contrast. So, this process effectively increases the diversity of our training data without needing to collect new images. So, after that, several convolutional neural network architectures are evaluated for their effectiveness in plant disease classification and detection, including VGG16, MobileNet, MobileNet V3 Large, GoogleNet, and AlexNet. So each architecture employs different strategies such as VGG16 with transfer learning, MobileNet without transfer learning, MobileNet with transfer learning, MobileNet with stepwise transfer learning, etc. So transfer learning is like taking knowledge gained from solving one problem and applying it to a different but related problem. Instead of starting the learning process from scratch for each new task, transfer learning leverages knowledge gained from solving previous tasks to improve learning and performance on new tasks. So, this approach is particularly useful when we have limited data for the new task. So, we will use the knowledge gained through transfer learning for plant disease classification. Similar to transfer learning, stepwise transfer learning involves a sequential process of fine tuning on multiple datasets, gradually adapting the model's knowledge to the target task. So, these are the algorithms and techniques we are using in this project. So, overall, the project wants to help farmers by making a tool that can quickly spot plant diseases. This helps farmers save their crops and support sustainable farming. It also gives useful information to researchers using deep learning. It tackles problems like not having enough labeled data. And the main aim is to make farming more precise and help ensure there is enough food for everyone. Now we will see the software and hardware requirements to execute this project. So hardware requirements are operating system of Windows, processor of i5 and above, RAM of 8 GB and above, and hard disk of 25 GB and above. Software requirements are application needed is Anaconda, primary language needed is Python, front-end framework needed is Flask, back-end framework required is Jupyter Notebook, database required is SQLite 3, and front-end technologies required are HTML, CSS, JavaScript, and Bootstrap 4. Now we look at the algorithms built. So these are the algorithms built for classification of plant diseases, and these are the algorithms built for plant disease detection. So in the base paper, author has proposed only these models for classification. For improved performance, we are proposing DenseNet 201 an exception for classification in this project. And in the base paper, author has performed only classification task. We are extending the project for detection also. So these are the algorithms used for detecting the plant diseases. Now we'll understand the algorithms which we have proposed. The first one is DenseNet 201. So the project uses DenseNet 201, a neural network used for image analysis, specifically in categorization. Its architecture allows for efficient feature reuse across layers, enhancing learning and performance. DenseNet 201 is used in a transfer learning approach, leveraging pre-trained weights from the ImageNet dataset. So this allows the model to recognize a wide range of features and patterns. The model's ability to detect subtle variations in leaf characteristics allows for precise classification of different leaf disease types based on input images. Now coming to exception. Exception is a deep learning technique. It is known for being good at understanding images. It does this by breaking down the process of looking at images into two main steps. First, it looks at different parts of the image separately. This is called depth-wise convolution. Then it combines these parts to understand how they relate to each other. This is called point-wise convolution. So this helps exception to understand images better and pick up on important details. One of its strengths is that it is really efficient at doing this, which is important when you are dealing with lots of images. Plus, it is great at figuring out what features in the images are important for making classifications. Another important thing about exception is that it can learn from other datasets before being used for a specific task. This is called transfer learning. So, this makes it super adaptable and useful for classifying leaf diseases. Now, coming to detection. So, YOLO, that is, you only look once, is a computer vision object detection algorithm that quickly identifies objects in images by splitting the input images into a grid and simultaneously predicting bounding boxes and class probabilities. Unlike traditional methods, YOLO processes the image just once, making it extremely fast. It predicts multiple bounding boxes and their associated class probabilities for each grid cell and then removes redundant detections using non maximum suppression. This results in a final list of detected objects along with their bounding boxes and probabilities. So these are different architectures in YOLO. YOLO V5 is known for its balanced performance between accuracy and speed. This version relies on a backbone network called CSP Darknet 53. It utilizes focus modules for downsampling and path aggregation network PAN for feature fusion, enhancing object detection across different classes. And YOLO V6 introduces a key difference by using EfficientNet L2 as its backbone network. Compared to EfficientNet used in YOLO V5, EfficientNet is known for its efficiency with fewer parameters, and it also employs a novel dense anchor box generation method to improve object detection accuracy. Now coming to YOLO V7, it uses a modified version of the Swin transformer architecture as its backbone. This architecture leverages self-attention mechanisms, leading to better feature extraction compared to convolutional neural networks used in prior versions. And the last one is YOLO V8. It is the latest version focused on facilitating performance comparisons with older YOLO models. YOLO V8 also introduces a unique loss function and an anchor free detection head, which are technical improvements to the overall detection process. So, we will be comparing all these models in the classification and the algorithms in detection, and will select the best performing model from each. So after doing this, after comparing the models, so exception model has outperformed all other models in classification, and YOLO V5 model has outperformed all other models in detection. So we will be deploying exception and YOLO V5 into the Flask. We will be executing the project using Flask web application. Before that, first we need to open the code folder which contains the project source code files. So this is the code folder and these are the contents I have in the code folder. So I'm opening data folder in which I have required plant, village and pepper datasets. I'm opening plant, village dataset folder. So here I have 15 classes of plant disease images folder in which I have respective images, plant disease images. So this is pepper bell bacterial spot folder in which I have pepper bell bacterial spot leaf images. Similarly, this is pepper bell healthy folder in which I have pepper bell healthy leaf images. This is potato early blight folder in which I have potato early blight leaf disease images. So similarly, I have respective images in other folders also. So we will be training the models, the deep learning models on these images. So before training the models, we will split this dataset, these images into two subsets, training and testing, that is validation sets in the ratio of 70 to 30. So after splitting the dataset into train and validation sets, this training and validation sets are now stored in this output folder. So now 70% of the images from all these class folders are into train set now, and 30% of the images from these folders are into validation folder. So train set is for training the models and validation set is for evaluating the model's performance. Similarly, in pepper dataset also, so these are the four classes I have: bacterial spot, healthy, leaf blight, and yellow virus. So I have respective images in these folders. These are bacterial spot images. These are healthy leaf images. These are leaf blight images. And these are yellow virus images. So we will split the dataset, the images from all these four folders into two subsets again, 70 is to 30 ratio. This train and validation sets are stored in output folder. So the 70% of the data from these four folders are into train set now. So on this data set, we will train the models, and 30% of the data set, the images are into validation set now. On these images, we will evaluate the model's performance. So these are the data sets used for classification. Now coming to detection. So we will be using plant village and pepper dataset for detection also. I'm opening plant village folder. Here I have YOLO V5, V6 and V7 folders. I'm opening YOLO V5 folder. I'm opening train folder here. So we can say I have two subfolders, images and labels. I'm opening images folder. These are the images of different leaf images, leaf disease images. So I have 15 classes of images here. And these are the annotation files. So each label file or annotation file corresponds to an image file in the images folder, providing details about the object's locations and classes within the image. So this annotation file corresponds to this image. This annotation file corresponds to this image. Similarly, each annotation file corresponds to an image in the images folder. So these label files often follow the YOLO format where each line represents a detected object. So here, this line is an object, this line is an object, and this line is an object. So we can see in this image, there are three objects detected. So each line specifies the object's class index. This is the class index, followed by its bounding box coordinates normalized to the image dimensions. So these are the bounding box coordinates. This is x limit, this is y limit, this is the width, and this is the height. Similarly, I have object class index followed by its bounding box coordinates normalized to the image dimensions in other annotation files also. So on these annotation files and images, we will train the deep learning models, the YOLO models, for detection. So here I have three folders: train, test, and validation. Train set is for training and training the deep learning models, as I mentioned earlier. Test set is for evaluating the YOLO model's performance. And validation set is for fine tuning the models for optimal performance. So I have same images and labels folders in test and validation folders also. And here I have YOLO V5, YOLO V6, and YOLO V7 folders separately. So each folder contains the same images, but they are annotated differently because each YOLO version requires its own specific type of image annotations for training and testing the models effectively. Having separate folders helps keep the dataset organized and ensures that each YOLO version receives the correct annotations it needs to function properly. Similarly, in Pepper folder also, I have three folders: YOLO V5, YOLO V6, and YOLO V7. So I have train and test folders. Train set is for training the models. Test set is for evaluating the model's performance. So in train folder, I have images and labels folders. In images folder, I have four different classes of images: leaf images. And in labels folder, I have annotation files. So this is about the dataset. This is sample folder in which I have test cases on which will make the classifications and detections. This is static folder. This folder consists of files related to CSS, JavaScript, and Bootstrap. This is templates folder. This folder contains all the HTML pages used in the project. It typically includes files like index.html, about.html, etc., which represent different pages of the website. This is app.py file. This .py file contains the information related to front-end logic. It includes code written in Python that handles server-side operations such as processing user requests, interacting with the database, and generating dynamic content to be rendered in the HTML templates. And these are model files which contain algorithm information. These files will be loaded into the project code during runtime to utilize the trained models. And this is Jupyter source file for classification task using Pepper dataset. This is Jupyter source file for classification task using plant village dataset. This is Jupyter source file for detection task using Pepper dataset, and this is Jupyter source file for detection task using plant village dataset. So these Jupyter source files contain combination of code, graphs, and outputs all in one place. It allows users to write and execute code in individual cells, making it a popular choice for data science. And this is signup.db file. This file is the database file used to store user information like signup details. Now copy the path of the code folder from the address bar of the file explorer. I'm copying it. Open Anaconda prompt. Use the command cd followed by a space and paste the copied path and hit the enter button. This command is used to change the current directory to the code folder's path. Now compile the app.py file using the command python space app.py. I'm typing python space app.py and hit the enter button. So this command will execute the Python script and perform a runtime check for any syntax errors or logical issues. After running the app.py file, the Flask framework will host the application locally at the default address, localhost, and port unless configured differently. So this is the local host and this is the port. Now copy the local link provided by the framework. I'm copying it and paste it into any web browser. I prefer Chrome. After pasting it, hit the enter button. So the home page of the project has been displayed in the browser. This is the front end built using Flask framework. So here we can see a sign up link, click on it. If we are new users, we have to register ourselves first. Fill in all these details and click on sign up button to register. And if we already have an account, we can directly log in by clicking on this link. So as I'm already a member, I'm clicking on this link. Here we have to give our credentials, username and password. I'm giving mine and click on sign in button. So it has redirected us to the prediction page. So here we can see a classification link, click on it. As I mentioned earlier, we can perform both classification and detection tasks in this project. First, we'll perform the classification task. So here we can see plant, village, and pepper data. So we have trained the deep learning models on both the datasets, plant, village, and pepper data. So we can execute the project using the algorithms built on these two datasets. So first we'll execute the project using the algorithms built using plant village dataset. So click on plant village. Now we have to upload the image here and the application will classify the leaf type and the disease type from the image. Click on choose file button. So from sample images folder, as we are performing the classification using algorithms built using plant village dataset, open plant village folder. So these are the test cases I have. So I'm uploading this image and click on open. The image has been loaded. Now click on upload button. It will take some time to load. So this is the uploaded image. And here we can see the classification, that is the leaf type is pepper bell bacterial spot. So the application has classified the leaf as pepper bell and the disease as bacterial spot. We'll try again. Click on classification link, click on plant village link, click on choose file. So this time we'll upload this image and click on open. The image has been loaded. Now click on upload button. This is the uploaded image. And here we can see the classification is the leaf type is pepper bell and it is healthy. So the application has classified this leaf as pepper bell and it is healthy. Click on classification, click on plant village, click on choose file. This time we'll upload this image and click on open. The image has been loaded. Now click on upload button. This is the uploaded image. And here we can see the classification, that is the leaf type is tomato leaf. It is mold. Click on classification, click on plant village. This time I'm selecting this image. Click on open. The image has been loaded. Click on upload. This is the image I have uploaded. And here we can see the leaf type is potato early blight. So similarly, we can try with other test cases also. We'll try one more. So I'm uploading this image. This is the uploaded image. And here we can see the leaf type is tomato and the disease is mosaic virus. Now click on classification link. This time we'll try with the algorithms built using paper data. Click on paper data link. We have to upload images again. Click on choose file. This time from sample folder, from paper folder. These are the test cases I have. I am selecting this image and click on open. The image has been loaded. Click on upload button. This is the uploaded image, and here we can see the classification, that is the pepper leaf is diagnosed with bacterial spot. So the application has classified the leaf disease as bacterial spot. Click on classification, click on pepper data, click on choose file. This time I'm selecting this image. Click on open. The image has been loaded. Click on upload. This is the uploaded image. And here we can see the pepper leaf is diagnosed with bacterial spot again. We'll try some more cases. Click on pepper data. I'm selecting this image. The image has been loaded. Click on upload. This is the uploaded image, and here we can see the pepper leaf is diagnosed with leaf blight. So this is the leaf image I have uploaded, and here we can see the pepper leaf is healthy. We'll try with this image. This is the uploaded image, and here we can see the classification, that is the pepper leaf is diagnosed with leaf blight. We'll try with this image. This is the uploaded image, and here we can see the pepper leaf is diagnosed with yellow virus. So similarly, we can upload any image from the test cases and can get the classifications. Now we'll see the detection task.
Thank you for watching video. For more projects, please visit our website www.trueprojects.in. For updates on latest project videos, please visit True Projects YouTube channel and subscribe.